You're watching Electrical Engineering Lectures channel. For more videos, please do like, subscribe and hit the bell icon for the latest notifications.
Now we move on to the conceptual implementation of ADC. So every ADC, the true design or the main categorical description of ADC consists of three blocks. The first block is C to D converter, which is basically the same thing that we have already discussed, the combination of sampling and zero order hold. This combination is referred to as C to D converter. The output is X of n, which is discrete time sequence having infinite precision and infinite number of levels along the y-axis. This X of n will be passed through quantizer, and the purpose of quantizer will be to convert that discrete time sequence into a digital signal containing finite levels that require finite precision. And the quantized signal X hat of n will be passed through coder to generate the data in the form of bit stream. It will basically map each quantized symbol into a number of bits so that the data can be treated as a true binary data. As we have already discussed the C to D converter in detail, containing sampling and zero order hold. Now we will move towards the second block of ADC, which is quantization or quantizer. Quantizer is basically a non-linear system whose purpose is to transform the input sample X of n into one of a finite set of prescribed values. So mathematically, it is a non-linear transformation. You input a data which is discrete time sequence, and it applies a non-linear transformation to convert that data into finite level sequence. How this is happening, we will see with an example. So let's say we have this continuous time sequence, a continuous time signal A, xa of t. First of all, we sampled it at a sampling period capital T. So after sampling, we get this result. Like this one. For example, we consider up to this point. This duration is capital T. So this is 0, T, 2T, 3T, 4T, 5T, 6T, and so on. This time is capital, the small t. So now this red sequence is named as X naught of n, XS of n. And this XS of n, when passed through a zero order hold circuit, it will make this dotted signal. Like this. I express with these dots the samples and then hold. So this blue one is the signal which is referred to as X naught of t, the output of zero order hold circuit. Now this X naught of t will be passed through the quantizer. What quantizer will do? The main thing is that quantizer has a specific number of levels, and what it will do, it will map each of the sample into one of those levels, and the number of levels is always finite. Let's say in this particular example, we formulate 4 levels. So if this is 0, this is 1, this is 2, this is 3, and this is 4. So we have got 4 levels, and each of these levels have a center line shown as the reference. So this one has this center line, the second one has this, the third one has this, and the fourth one has this. So we just number the levels as 0, 1, 2, and 3, right? So now what quantizer will do, it will take each sample and map to the nearest green line, right? So starting from the first sample, let's say we consider this one. So the nearest line is this. So I am showing it with a cross just to differentiate. It will map it here. The second one is again mapped to the same point over here. And the third one will be mapped to this point. The next one will also be mapped here. And the next one will go over here because it is the nearest one. The lower one is far. And similarly, now you see, for this particular sample, the next one, both the green lines, the upper one and the lower one, are at the same distance, so it can go anywhere. Let's say it goes to the upper and the last one over here. So in terms of values, let's say the actual values were, first of all we write the actual values which are the sampled. So the actual value, first one was, let's say 0, and we just also scale the voltage level also. So writing the voltage level here, you see this is 0, 1, 2, 3 and 4. So this is 0.5, this is 1.5, this is 2.5 and this is 3.5. So the actual sample has got the value of 0. Let's say 9. The next one has got approximately the value of 1.3. The next one has 1.4 and the next one has the value of 2.1, and then the next one has the value of 3, and then it has got the value of 3.5. So these are sampled values denoted by x of n. Now what will the output of quantizer? We call it as x hat of n. So x hat of n will be the quantized values shown by these red crosses. So in place of the first sample, it will generate 0.5 as per the nearest level. For 0.9, it will map it again to 0.5, and 1.3 is mapped to the level 1.5, and then 1.4 is also mapped to 1.5, 2.1 will be mapped to 2.5, 3 will be mapped to 3.5, and 3.5 to 3.5. And in terms of levels, if we write here as 0.5 is corresponding to level 0, it is also corresponding to level 0, then it is level 1, it is also level 1, it is level 2, and this is level 3, and this is level 3. So this is the output of quantizer, x hat of n. You can also describe it in terms of number of the level index. So you see, we have converted that discrete time sequence requiring infinite precision into finite number of levels. So the output of the quantizer will always have a value from these 4 values, 0, 1, 2 and 3. No matter what the actual value of the sample sequence was, the output of the quantizer will have one of these 4 values, either 0, either 1, either 2, either 3. See, now what is the maximum error? What is the maximum error that a quantizer can give? That error can be seen by this diagram. You see, you consider this particular point. When we were at this point, we said it can go on the upper green line as well as on the lower green line. So at max, what is the amount of error? The amount of error is 0.5. The magnitude of error is 0.5. Given the height of the level is 1 volt, the maximum error is 0.5. So if we generalize this point and we say that if the level height is delta, then maximum error will be delta by 2. So this is the maximum error. That is point number 1, right? E max will always be delta by 2. It means if we increase the number of levels in a given duration, then definitely delta will be reduced, and then if delta is reduced, error will be reduced at the same time, right? So if you see the dynamic range of this ADC, we call it as 2xm in terms of voltage, where xm is half of this voltage. In this particular case, let's say xm is equal to 2, so 2xm will be equal to 4. So if the maximum dynamic range of the ADC is 2xm, if dynamic range is 2 times xm, number of levels is, let's say, equal to L, and the level height level height is equal to delta, then we can write an equation that L multiplied by delta will be equal to 2 times xm. Number of levels multiplied by height of each level, it will give the complete dynamic range, and that is already equal to 2xm. It means we can write delta is equal to 2xm divided by number of levels, right? So this is a very important equation in the design of ADCs. It is giving you the level height in terms of the dynamic range and the number of levels. So the next stage of ADC after quantization is encoding. We need to convert these numbers. We need to convert these numbers in the form of bits. Now the question is, how many bits are required to represent these numbers? The numbers are 0, 1, 2 and 3. So to represent all these numbers, we will require 2 bits. Similarly, if you increase the number of levels, for example, I say if I increase the number of levels to 8, then I will require 3 bits to represent each one of these samples. So it means they are related with the number of levels, right? And if you see what is the relationship between them, let's say, let the number of bits to represent one sample is b plus 1, then number of levels will be equal to 2 raised to power b plus 1. So if we require 2 bits to represent the levels, then number of levels will be 4 and so on, right? So if you substitute this value of L in the above equation, then delta comes out to be 2xm divided by 2 raised to power b plus 1, and this 2 will be cancelled out. So delta will be equal to xm divided by 2 raised to power b. That is another form of the same equation, which is relating the delta in terms of the number of bits per level, right? Now the representation in binary can be done in any way. One of the method to represent the quantized samples in terms of bits is 2's complement. You can use any method, but how 2's complement proceeds? In 2's complement, let's say the sampled after the quantized sample comes out to be 1 over 4. Now 1 over 4 can be represented because it is a positive number, and in 2's complement the first bit is used to represent the sign, and because it is positive number, so I will say I can write it as 0. This is, for example, the decimal point 0, 0 and 1. So it will be equal to 0.25, and the conversion is again as you convert a binary number into decimal number. Similarly, if I have minus 1 by 4, so I can write here 1 and here 1 and 1, because 1 is for negative. So the overall weight will become minus 1 plus the weight of this one will be 0.5 and the weight of this one will be 0.25. So it will become minus 1 plus 0.5 plus 0.25 to give the result as minus 0.25. So in this way you can represent the quantized sample in the form of binary stream, right, using 2's complement. Now after discussing the complete flow of ADC, now let us discuss more about the error of the quantizer, because this is a very important parameter that needs to be discussed in the design and selection of ADC, right? So the error E of n between the input and the output of quantizer is given by this equation. E of n is equal to x hat of n, which is the quantized sample, minus x of n, which is the output of zero order hold. So the difference between them is the error. So you can simply assume that this quantizer is actually a source of noise. If the input is x of n, if you add E of n into this x of n, then you will be getting this one. So the main thing is, what is the characteristic of this error? This error can be modeled as a uniform random variable, because it is a random quantity, and a famous model to model this quantization error is uniform random variable, and the PDF of uniform random variable is in the form of a rect function with a starting point and an ending point. As we have already discussed, that the maximum quantization error can be delta by 2 in either direction. It can be up to delta by 2, and at minimum it can be minus delta by 2. So the overall range of this quantization error is from minus delta by 2 to delta by 2. So we can model this quantization error as a uniform random variable starting from minus delta by 2 up to delta by 2, and the amplitude of any uniform PDF, because in general if you draw a uniform PDF like this in an interval a to b, then the height of this PDF will be 1 over b minus a. So here if you replace a and b with this value and this value, you can get the maximum value of this uniform PDF as 1 over delta. Right? So this is basically the model of this quantization error. Now using this quantization error model, you can find out the SNR of ADC. Now let us discuss the same quantization error model over here. First let me draw the PDF of E of n over here in the form of uniform PDF starting from minus delta by 2 to delta by 2 and 1 over delta over here. Right? So the mean value of this PDF, expected value of E of n for uniform random variable, it is given by a plus b over 2. In our case it will be 0, because if we put a equal to this and b equal to this, we will get straight away 0. So the mean value of this quantization error is equal to 0, and whenever the mean value of any random variable is 0, the power of that random variable is given by simply the second order moment or the variance, right? So the variance of E of n, as a standard formulation, it is given by b minus a whole square over 12, right? So b minus a whole square over 12, in our case it comes out to be delta square over 12. If you solve by putting the value of a and b, you will get this one. Now this is the power of noise. So if you find out what becomes the SNR of ADC, just to see what are the controlling parameters that change the SNR, so that it may be beneficial for us whenever we are going to work with ADCs, how to select a particular ADC which can fulfill our needs or which can provide a requisite amount of SNR. So it will be power of signal divided by power of error, which is noise, because error is acting as noise. So the power of signal is given by simply, let's say if the input signal was x, so it will be simply x square by using a standard 50 ohm model, and the power of error is delta square over 12. Now if you put the delta value, because delta was equal to xm divided by 2 raised to power b, if you put this value over here, SNR comes out to be x square divided by xm square over 2 raised to power 2b, and you take 12 over here, and if you rearrange the same expression, I can write SNR as 12 multiplied by 2 raised to power 2b multiplied by x square divided by xm square, where xm is basically one-sided or peak value of x of t, and b is the b plus 1, sorry, because as per our model, and d plus 1 is the number of bits per level. Now from this expression, it is very much clear that SNR is proportional to P, which is the number of bits. Straight away, it means as you increase the number of bits, SNR of ADC will improve, and as you increase number of bits, it means we are increasing number of levels, and definitely it makes sense that increasing number of levels will reduce the quantization error, and thus it will improve the SNR of the resulting ADC. So this capital B is very much important, and it is used in the specifications of ADC. You must have heard the name, like we say 10-bit ADC, 12-bit ADC. So that bit is basically defined by the same number. So we usually refer to as ADCs in this way, like 10-bit ADC, etc. So This is the way we define ADCs. Now you can convert the same expression into log scale to have further understanding of this. So the same expression is written over here, and we have just taken 10 log of this equation to make this output. Now you see we have three terms over here. The first term, the second term is constant. It has nothing to do with any parameter. The first term is very important, and it clearly saying that increasing 1 bit in the design of ADC will improve the SNR by 6.02 dB, right? So approximately 6 dB increase in SNR for each added bit. And remember, each added bit will double the number of levels. For example, if we have 2 bits, then the number of levels are 4. If we increase 1 bit and we make 3 bits, then the number of levels become 8. So it will be 4 into 2 equal to 8. So that means the number of levels are doubled, and so on. And secondly, full scale amplitude XM of a particular ADC is always fixed because it is the dynamic range of ADC. You cannot provide any signal out of that dynamic range. If you provide signal out of dynamic range, it means a lot of quantization error and overflow will result. And selection of signal power or its peak amplitude is very important to guarantee better SNR to avoid any kind of overflows and saturations, and thus reducing the quantization error. Now finally in this lecture, let's have a quick glimpse about the non-uniform quantization, because the quantization we have discussed so far belongs to the category of uniform quantization. Non-uniform uniform quantization means the height of each level is the same. There are cases in which we do not want to have same height for each level to increase the resolution of ADCs. In those cases, we go for non-uniform quantization where the height of each level is not the same. In those cases, it is referred to as non-uniform quantization. For example, this strong signal, we can afford a uniform quantizer. But if the signal is weak, like this one, it requires more resolution. So it means if we still use uniform quantizer, this signal will only be limited to 2 or 3 levels, and there will be a lot of quantization error, right? So to further increase the resolution, we reduce the level heights in those points where we want to have more resolution. So this is referred to as non-uniform quantization, right? So that's all about the design of ADC, its fundamentals, and uniform and non-uniform quantization. Thank you for watching.